Hello my dear students, welcome back to the session. Students, last class we discussed RLC series circuit, RC parallel circuit. Then let us look at RLC parallel circuit here, okay? So here, you know the admittance, right? Admittance is nothing but what? G plus J BC minus BL. But we do not know whether BC is greater than BL or BL is greater than BC. That's why I take case 1. So the first case here, let us take BC greater than BL or BL greater than BC. Let us say first we'll take BL greater than BC. So BL greater than BC, what does it mean? BL greater than BC means, okay, is it inductive or capacitive? Okay, BL greater than BC is inductive or capacitive. If BL is greater than BC, some people think like this. Let's look at this. Some people may think like this. Okay, XL less than XC. Therefore, when XL less than XC, we learnt that it is a capacitor circuit. Agree, all of you? Like this, some people may think. But look at this. This XL less than XC or XL greater than XC is valid only for a series circuit, not for a parallel circuit. For a parallel circuit, when BL is greater than BC, look at this Y will become, when BL is greater than BC, okay, this part will become negative or positive? Definitely negative, right? So therefore, it becomes G minus JB form. G minus JB form, is it for inductive or capacitive? It is for inductive. Therefore, BL greater than BC is still inductive for a parallel circuit, but XL greater than XC is inductive for a series circuit. You understand all of it? Okay. So therefore, students, here you must understand, note, put a note and write down here. Okay, I can give you a point. In a parallel circuit or in a series circuit, XL greater than XC, nothing but BL less than BC, inductive. XL less than XC, nothing but BL greater than BC. Here it is capacitive, no doubt. Understand? In a parallel circuit, now you must take susceptances, not reactances. Understand? Whenever you take a parallel circuit, you must always compare susceptances, not reactances. So BL greater than BC, that means XL less than XC, that means it is inductive. You understand, all of you? Then BL less than BC. Yes, here you can compare. If BL greater than BC, in a parallel circuit, no doubt XL less than XC. Understand? So XL will be greater than XC in this case. It becomes capacitive. So what do you understand from this? When you deal with a series circuit, you always compare the reactances. Obviously, you are comparing susceptances there itself. Yes or no? Similarly, in a parallel circuit, you always compare susceptances. Okay? And of course, if BL greater than BC, in this context, XL will be less than XC, no doubt in that. But never compare susceptance here and in reactance here. Understand, all of you? Okay? So this is very, very important point. So therefore, still it is an inductive circuit behaving like an inductive circuit or lagging power factor circuit. Understand? Therefore, what do you get from this? Y is equal to G plus J, okay, minus, because this is negative. So negative, let's take it out so that in this, you know, the inside the bracket, that quantity will be a positive value. So BL minus BC. So it becomes now root G square plus BL minus BC whole square at an angle of tan inverse, minus, right? Minus tan inverse. Minus tan inverse BL minus BC by G. Clear? If you multiply on both sides, now I am taking V is equal to V at an angle of 0. Okay, then I is equal to here in this context. Okay, let me take here in this context V is equal to V at an angle of 0. Then obviously I becomes I at an angle of, okay, minus 5, because current lags behind the voltage, then it should be a negative angle. Understand all of you? Okay, so if I multiply V into Y is equal to V into G minus J V into BL minus BC. Clear? So if you take now this one, then you have I is equal to, this is IR, I can take magnitude directly, minus J, okay, IL minus IC. So I got a chance here to take directly the magnitudes because the angle of V is 0. Therefore, V or mod V both are same. Therefore, IR and mod IR both are same. Yes or no? So therefore, is equal to, I get now IR square plus IL minus IC, okay, whole square at an angle of, okay, at an angle of, here in this context, minus tan inverse IL minus IC by IR. Yes or no? Okay, so like this we'll get. Like this we'll get. 1 second. So here, what about S again? S is a complex power. Similarly, you get now V I cos phi. Angle 5 negative conjugate will become positive. Therefore, plus J V I sin phi. This is an active power. This is the reactive power. Inductive reactive power. P is equal to Vi cos phi. This is the active power supplied by the source. But active power consumed by the load or by the resistor, you can keep it now. You can write IR square into R or VR square by R. In this context, VR and V both are same. Yes or no, all of you? Okay, because it's a parallel circuit. So VR and V both are same. Similarly, QL, VI sin phi. IL square. So this is not QL simply. This is QL minus QC. Yes or no? Because it is a parallel RLC circuit. You have both inductive reactive power and capacitive reactive power. But who is dominating here? Inductive. Yes or no? That is why you get QL minus QC. So IL square into XL or VL square by XL. XL or into BL you can write if you want. So VL square is nothing but V in this context. So QC is nothing but, it's not actually VI sin phi. It is QL minus QC is VI sin phi. So let me write clearly here. Let me write clearly here. This is QL and QC. IC square into XC. Here I can write V square into G. Here I can write V square into BL. Here I can write V square by XC, V square into BC. Here you generally write here lagging reactive power, here leading reactive power. That's it. Okay. Please write down, all of you. Then we will see the phasor diagram corresponding to this quickly. In a series circuit, after writing this, you can note down this. Okay. First you complete that and then we'll draw the phasor diagram. Then later only you draw this. You can note down this. Okay. Wait for some time for this particular part. You finish only up to this particular part. When you draw the phasor diagram, I told you already that you need to list out all the phasors to be represented on the phasor diagram. Yes or no? Then what are the phasors that you have in this IR? Okay. IL, IC, and you also know that I is equal to IR plus IL plus IC. Yes or no? Okay. First, let me take V as a reference phasor, because we know that parallel circuit V must be taken as a reference phasor, and this is IR, V into G, this is IL, V into BL, this is IC, V into BC. Yes or no? Yes or no? All of you. This is IR into G. Now, if I add this phasor at the tip of this IL, this is IC, right? So this is IL, this is IC, then the resultant up to this part is what? IL minus IC. Clear? Then this is the total resultant. This is I, nothing but root IR square plus IL minus IC whole square. These are all magnitudes, okay? Now, angle difference between the V and I is nothing but power factor angle or power angle or whatever it is. Okay. So now, if you divide each phasor by V, okay? If you divide each phasor by V, now what do you get here? This is G, this is BL minus BC. What about this? This is Y. This theta nothing but phi. Then Y is equal to G square plus BL minus BC whole square. If you multiply each phasor by V, here each phasor is divided by V, but now you are multiplying with V. Then if you multiply with V, what do you get? P is equal to V square into G. But it is inductive. Inductive means the power will be in the first quadrant in the complex plane. And this is P V square into G. This is QL minus QC. V square into BL minus BC. This is S. This is phi. S is nothing but root P square plus QL minus QC whole square. Clear? So this is a phasor diagram for RLC parallel circuit. All of you note down. And you also note down this part. Okay? Note down that part. Let me remove this meanwhile. Finish, okay? I hope you have finished this part. Phasor diagram. All of you understand? We have taken V as a reference phasor, then IR, then IL, because current lags behind the voltage, and IC, current leads the voltage by 90, current to capacitor, right? So like that. So now let's take the case 2. Case 2, right? So case 2. BC greater than BL. What do you mean by BC greater than BL? It is a capacitor circuit. It is behaving like a capacitor circuit or leading power factor circuit or leading power factor circuit. Then Y becomes G plus J BC minus BL. Okay. Then it becomes root G square plus BC minus BL whole square. So please proceed along with me. Don't wait, because already you have experience. So no need to wait until I finish. Okay. Now you please write along with me. I don't give you time again after this. Okay. So please note down. Tan inverse BC minus BL by G. So this part you can note down along with me, okay? Then you multiply with V, then you directly get I is equal to IR plus J. So what is the assumption here? V at an angle of 0, then I will become what? I at an angle of plus 5. If you take 0, then I will become plus 5. J, IC minus IL. Root IR square IC minus IL. Here also these are all magnitudes only, okay? They're all magnitudes only. Yeah. At an angle of tan inverse IC minus IL by IL. That's it. S will also become V into I conjugate VI cos phi minus J, because conjugate you are taking to current, then current angle is already phi, but conjugate of it is minus phi. Therefore, J minus J VI sin phi. This is P. This is QC minus QL. Because here in this context, the QC is dominating because BC is dominating. Yes or no? Okay, capacitive circuit it is. So what is P you know very well. Write down along with me, okay? VA cos phi. So IR square R, VR square by R, or VR square into G, or V square into G, because VR, V both are same in this context. But remember always the formula IR square, VR square only. Okay? QL is IL square into XL, or VL square, nothing but V in this context, into BL, lagging. Similarly, QC also, IC square into XC, or V square into BC, leading. Okay, note down? Note down, note down. I just draw a phasor diagram also here. Note down quickly that part. Note down. And I will draw here the phasor diagram. I will also remove this part. So let me draw the phasor diagram. Better I draw here, okay? So all the phasors, I think already the phasors are available here. Let me draw here. V, IR, IC, IL. Okay, so we know what is this actually, V into G, V into BC, V into BL. Yes or no? Draw this at the tip of it, and it gets cancelled this portion, and finally you are left with what? Okay, IC minus IL. So this is the resulting phasor, that is I, this is angle phi. Clear? So V into G. Okay, so very clear that root IR square plus IC minus IL whole square. Divide again each phasor. Definitely the admittance for a capacitive will be in the first quadrant. Angle theta nothing but phi. G square plus BC minus BL whole square. For a capacitive circuit, the power will be in fourth quadrant. So V square into G. QC minus QL is nothing but V square into BC minus BL. So S is equal to root. Write down, all of you, write down. QC minus QL whole square. Clear? So like this, we can draw the phasor diagrams. So I hope you have finished this part. Let me remove it. Similarly, case 3, BL is equal to BC. It behaves like a resistor circuit, unity power factor circuit. So then Y is equal to G, I is equal to IR, S is equal to P. Phasor diagram. This is V, this is IR, this is IC, this is IL, V into BL, V into BC, V into G. Since BL is equal to BC, IL is also equal to IC. Then it becomes like V, the total current I will become IR in this context. Okay, so this is the phasor diagram for the condition BL is equal to BC. BL is equal to BC. So this is a phasor diagram, and all these three conditions we have mentioned for RLC parallel circuit. Similar to RLC series circuit, we have done this part. Okay. So this is how you analyze all series and parallel circuits, and one must be having on fingertips all this. You should not really search for the formulas and the phasor diagrams. Okay, you should be able to apply all these whenever you come across the problems. That comes only through practice, I'm telling you. Okay, twice and thrice without looking at the notes, you must be able to write all this part, fundamentals of AC circuits, whatever I've explained. RLC, series and parallel circuits, you must be able to write every expression easily. Then only you will have a flexibility. Okay, so quickly note down this part. Doing the problems. Okay, so first one is, can put a note. First one is, okay, I have a practical coil, choke coil, practical inductor, and one series resistor is connected across, or in series with, one resistor is connected in series with the coil. So if you see that a choke coil or a practical inductor, nothing but what? Choke coil with a series resistor, Clear? So how it looks like? Choke coil is something like this. You know very well, choke coil will be offering resistance R smaller. It's a very, very small value. This is L. Understand? This is called a coil. Choke coil. Now it is in series with a resistor connected. in series with a resistor. Now this hole is excited by a voltage source, okay, like this. Now assume that with the help of this MI type meter, MI type means what? Moving iron type meter. I measured the voltage here. Say this is V2. Voltmeter reading is V2. I measured the voltage here. Say this is V3. I measured the voltage here. Say this is V1. Okay. This is V1. Understand? Okay. Now this is V1, V2, V3 are the voltmeter readings. Assume that there is an ammeter placed here. Now these are all values are available, let us assume. Because this is an experiment actually which you do generally. I don't know how many of you have done in network theory laboratory to find the parameters of the choke coil. Okay. The voltage across this particular one is VR, let us say, and the voltage across this particular L, assuming that, okay, because this is not known actually. These are not separable actually. This is combined. The choke coil is combined, right? But if you assume that it's a equivalent circuit is RL series circuit, then assuming that the voltage across this L is VL, VR is the voltage across that small r. Okay. Now it's very clear. This is say current I. Okay. Now can I say something like this? From this I can understand some relations that, okay, V2 is in phase with I. VR is also in phase with I. VL, okay, VL leads I by 90 degrees. Yes or no? Because voltage across the inductor leads current to the inductor. What is current to the inductor? I only. Now V3. Now assume that the coil impedance is something like Z1 at an angle of theta. Okay. The coil impedance is Z1. The overall impedance, let us say Z. Okay. Let us assume that. Now V3 leads I by how much angle here? Usually what is the phase difference between V3 and I? V3 and I phase difference will be, because you know that V3 and I phase difference is called power factor angle. But power factor angle is also same as what impedance angle. Can I say this Z1 because Z1 is nothing but V3 by I? The phase difference between V3 and I and the phase angle of Z will be same. We already seen that. Okay. Therefore by theta. Clear all of you? Okay. Now V1, because it is a lagging power factor circuit, current always lags. Then V1 and I, when you compare, let us assume that the angle difference between V1 and I is phi. Since it is an inductive circuit overall, current lags, therefore V1 leads I by some angle phi. Is it clear? From this particular diagram, we can conclude these points. Yes or no, all of you? Okay. Well, now let us draw the phasor diagram. We'll find some interesting points here. Remember, this V1, V2, V3 all are what? Given in this circuit what? Only magnitude. That means MI type meters are measuring the voltage and current values. Okay. Now let me draw the phasor diagram clearly. What is the phasor diagram? Let us see. The phasor diagram, when I draw, let me take current because the series circuit. Current is taken as a reference phasor. First, let me draw, because V1 is nothing but when we draw the phasor diagram, we generally take, okay, the relation V1 is equal to V2 plus V3. Phasor addition I am taking. But what is V2? V2 is in phase with I. Therefore, this is V2. What is V3? V3 leads I by theta, and it can be added at the tip of V2 to get V1. So therefore something like leads, this is V3, and how much angle it makes? Theta. So this is nothing but actually parallelogram theorem. Like this is also angle theta. Yes or no? But what is actually V1 is, this is V1, it makes an angle phi. Clear? When you have phase A, let us say phasor A, phasor B, and the resultant phasor is C. I think we have already seen the parallelogram theorem, the formula we know very well. So what is that actually here? V1 square is equal to V2 square plus V3 square plus 2V2 V3, all are magnitudes, okay? All are magnitudes, cos theta. Yes or no, all of you, okay? All are magnitudes. So even if I mention or not, all are magnitudes, don't forget that. So from this we understand that cos theta is equal to, what is cos theta actually here? Cos theta is nothing but, okay, look at this angle of Z1 theta, that is angle of the coil, is also phase difference between voltage across the coil and current through the coil. Usually voltage and current phase difference is called power angle or power factor angle. If you apply cosine to it, you call it power factor. Therefore, you call cos theta is nothing but power factor of the coil. Okay, so what is its value? You will come to know here V1 square minus V2 square minus V3 square divided by 2 times V2 and V3. Is it clear? All of you? So this is what cos theta. And you can also find the angle of this, that is angle phi is equal to tan inverse sum of vertical components by sum of horizontal components. There is no vertical component because it's making an angle 0, but there is a vertical component for it. So V3 sin theta, V3 sin theta by, let me write clearly here, V2 plus V3 cos theta. Understand all of you? Okay. You can also observe one important point. Tomorrow I want to find, let us say, R and L values of this choke coil, separation of parameters of the choke coil. Okay, this we have already learnt when we discuss some fundamentals. Okay, we discussed this part in our inductors and capacitors chapters. We are going to find these R and L values. Okay, going to find R and L values in the laboratory when a choke coil is given. Using the phasor diagram approach, it's very, very important. Okay, so what is that actually? If I find VR, what is VR actually? V3's horizontal component is nothing but VR. V3's vertical component is nothing but what? VL. That means you see here, V3's horizontal component, this is VR. Yes or no? This is VR. This is actually you get like this. Okay, this is VL. This is VR. So V2 plus VR is nothing but the total voltage of the real part of this total voltage, V1. And vertical component is there only for this coil because there is no vertical component for it. So finally you got here, let us say VR is nothing but VR, okay, VR is nothing but V3 cos theta. VL is nothing but V3 sin theta. Yes, I can find now from this, if I know ammeter reading, that is current I, then R can be written as VR by I, yes or no? Nothing but V3 cos theta by, okay, I. And XL is nothing but VL by I, that is V3 sin theta by I. That's it. Understand? So these are all very, very important relationships, okay? So please note down. This is the practical inductor, that is nothing but choke coil with a series resistor. You can easily recognize whenever this kind of diagram is given in the exam. Understand? And what is V1, V2, V3? Only RMS magnitudes of the voltages read by MI type meter connected across these okay, elements. Note down. Hope you have finished this, okay? This part I am removing. Please proceed with that. I take another case here. Now let me take a second case. Case 2 or second part. A practical capacitor with a parallel resistor. Okay, how it looks like? Yes, now I am taking a current source for my convenience, because parallel circuit, if you take current source, that will be more convenient to analyze. This is a practical capacitor. You know that what is a practical capacitor? An ideal capacitor with a parallel resistor. Okay, this is C. This is R1. This is R. This is I. And the voltage, let me write it. Let us say G1, otherwise parallel circuit generally we take conductances. So this is G and this is the voltage V, let us say. Okay. So the voltmeter reading or ammeter reading, now this is the voltmeter reading. This is an ammeter reading. What is an ammeter reading here? Let us say now here is an ammeter. Its value is I. Here is an ammeter. Okay. I let us say, yeah, I1, otherwise I1, A1, A2, there is nothing but I2, A3, nothing but what? I3. Okay. So this is what current flowing through this resistor, assuming that, okay, IR and this is IC. Clear? So from this, we can also draw certain conclusions, like what we did in the case of a practical inductor with a series resistor. It's very, very important. All of you look at this. So don't write. I'll just explain you clearly. Don't write. Similar to what we have done in the case of practical inductor, we can also analyze the same. Okay. So in exam, you may get the questions on this kind of circuit: a practical capacitor with a parallel resistor or a practical inductor with a series resistor. Practical capacitor with a parallel resistor or practical inductor with a series resistor. Okay. So let us take some relationships here. What are the relationships you have? Look at this. What are the phasors you have? V and I1, I2, I3. Yes or no? So first let me take I2. I2 is in phase with V. Yes or no? Parallel circuit, let me take the V as a reference phasor. Then assume that this is Y1 at an angle of theta. Okay, that admittance. What is the admittance actually here? This is not just simply C, this is, let us say, BC plus JBC. Okay, plus JBC when you have a frequency. Otherwise, it is an RC series circuit. You understand, all of you? So just to make you understand, I have just shown here plus JBC. Therefore, it is Y1. Okay, so C. Now, here I3 or IR, otherwise IR is also in phase with V. IC leads V by 90 degrees. Next, I3 leads V by angle theta. Then I1 also leads V by some angle phi. Understand? Now let me draw the phasor diagram. I am taking now the voltage phasor as a reference phasor. Now what is the relation actually you have? I1 is nothing but what? I2 plus I1 is nothing but what? I2 plus I3. The current is getting divided. Okay. Now this is I2. Now this is I3. Angle theta. Now this is what actually you have I1. It makes an angle phi. Now similar to what we have seen just now, you have V, just a minute, you have I1 square is equal to I2 square plus I3 square plus 2I2 I3 cos theta. Yes or no? This is what theta between I2 and I3, the resulting phasor magnitude will be written like this. Parallelogram theorem only, I am writing nothing else. Okay. So cos theta will become what now? I1 square minus I2 square minus I3 square 2 times I2 I3. So cosine of angle difference between the voltage across the practical capacitor and current through the practical capacitor. This is an ideal capacitor, but this is a practical capacitor total part. So that cosine when you apply, it's nothing but power factor. This is the power factor of practical capacitor. Understand? Okay. Now, angle phi is nothing but what? Tan inverse of. Angle phi is nothing but what? Sum of vertical components, sum of horizontal components you can take. Horizontal components, vertical components when you take. This is actually, IC. This is nothing but actually here what? IR. This part. So IR and IC will give you I3. Look at this. IR and IC. This is a parallel RC circuit. This is a total current supplied to the parallel RC circuit. Now what will happen? This IR and IC phasor addition will give you what? I3. Yes or no? Okay. This is I3. I3 can also be written as IR plus IC. Yes or no, all of you? So you already drawn RC parallel circuit. So this is V, then IR and IC will give you I3, but already I2 and I3 will give you I1. Like that you must analyze the circuits. Okay, like that you must analyze through phasor diagrams concept. Okay, so phi is equal to tan inverse of vertical components. What are the vertical components you have? I3 sine theta by horizontal component I2 plus I3 cos theta. Understand all of you? Okay, this is very, very important. Now another important one is now you know that R is equal to, you already know that that G1. What is G1 actually here? I would like to find G1. G1 is nothing but, okay, IR by or IR into V, let us say. Okay, IR into what? V. Yes or no? What is IR actually here? What is IR? IR is nothing but what? I3. What is it? Cos theta into V. What is BC? IC into V. But what is IC? I3 sine theta into V. Clear all of you? Okay. So if I know all these ammeter and voltmeter readings, I can find even what is G1, what is BC also. Once I know BC, if I know the frequency of the supply, I can also find the capacitance value. Okay, so capacitance value you know very well, 1 by omega into BC. But if you know BC, then if you know omega, then only it is possible to find C. I can find BC here, but I must be given omega. Clear? So please note down. Please note down. The relation what we have written here is, okay, by divided by, right, not multiplication. Clear? IR by V, I3 cos theta by V. IC by V, I3 sin theta by V. Okay, clear. It's not multiplication, it is division. Okay. Down clearly, all of you. Can you find the power of that capacitor? Yes, you can find, right? What is the power consumed by the practical capacitor? Average power. You can write that IR square into R into R1 or else by G1. Yes or no? But what is IR actually here? IR is nothing but what? I3 cos theta whole square by G1. Similarly, in case of practical inductor also, what is the power consumed by the practical inductor of the choke coil? What was the power actually there? You can write, please note down in the previous case also, the power of the coil was VR square by R. But VR was V3 cos theta whole square by R. So please note down this part in the previous one, choke coil, previous one. In the choke coil, in the last, okay, end part, you can write power of coil is nothing but VR square by R, V3 cos theta square by R. So they're all very, very important to be understood. And we'll see some more also here. Quickly note down that I can take this off, okay. Hope you have written this also. In case of choke coil, please write this, okay. The power consumed by the choke coil can also be determined. Third one, when you have two impedances Z1 and Z2, R1 plus JX1, R2 plus JX2. Z is equal to Z1 plus Z2. This is R1. This is X1. This is R2. This is X2. This is Z2. This is Z1. This is theta 1. This is theta 2. But this becomes what? Z. The horizontal component of this is nothing but R1 is equal to Z1 cos theta 1. X1 is Z1 sin theta 1. Then R2 is equal to Z2 cos theta 2. X2 is equal to Z2 sin theta 2. Similarly, the effective resistance will become what? R plus JX, let us say. Then R will become, okay, this R is nothing but what actually here? R1 plus R2. And also Z cos theta. X is nothing but what? X1 plus X2. Then Z sin theta. Clear? So therefore, look at this. What is this? Is it not R2? Yes or no? R1, Z1 cos theta 1 plus Z2 cos theta 2 will give you R1 plus R2. And this is nothing but R. This is X1. This is nothing but X. Okay? This is actually called theta. Clear? Okay? Like that, similarly, even for admittances can also be written. Okay, so I stop the session here, and we will see the remaining part in the next session, Y1 and Y2.